Welcome to lecture number 26 for ECE 341 Random Processes. In this lecture, we're going to go through a bunch of examples of using a t-test with a single population. Now, the previous lecture introduced the student t-distribution. What that distribution assumes is that you have a normal distribution where I don't know the mean, I don't know the standard deviation, but I can collect data. From the samples, I then estimate the mean and variance, and from that, I get a t-distribution. Now, what I can do with the t-distribution is I can do a single-sided test, such as the probability that a given die roll will be bigger than, say, 20. I can do a two-sided test. Can I bracket it? Where will the die roll be 90% of the time? And I can do a 90% confidence interval for a population's mean, such as what is the average of rolling those dice. So in this lecture, we're going to do a couple of different examples. One, we'll look at the weather in Fargo and ask, is June going to break 100 degrees this year or next year? I can ask, what is the 90% confidence interval for the high in June? I can roll 10 six-sided dice and find out what's the probability that the 10 six-sided dice will be bigger than 44, what's the 90% confidence interval when rolling all 10 dice, and what's the confidence interval for the average of 10 six-sided dice. We'll look at some previous lectures. Previous lectures, we looked at 5-card stud poker. I deal out a poker hand, actually deal out 100,000 poker hands, and see how many times you get a full house. From that, what is the 90% confidence interval for the number of hands I'm going to get that's a full house? And what's the probability that I actually get a full house? And finally, we'll look at 1K 5% resistors. Now, previously we assumed those have a uniform distribution anywhere between -5% and +5% in nominal value. Is that a valid assumption? Is that correct? So that's what we're going to do in this lecture. Do a bunch of examples of things you can test with a t-test. So starting out, let's look at the weather in Fargo. So to get this data, you can go to Hector Airport. That's also linked here on Bison Academy. Go under t-distributions. Actually, it's under lecture 21. I can pull out the data for like the high in Fargo. This is from wonderground.com. Since 1942, they've been measuring weather in Fargo from Hector Airport and recording the month high, average, and low. This is summarized in these tables. Then using those tables, I can do some calculations. And for the monthly high in Fargo, this is the month, the mean, the standard deviation for the data, and the number of data points. And you can pull that up, analyze yourself. It changes year by year, because each year we get more data. But there's the data as of 2025. Now, we've used this in previous lectures. In previous lectures, we ignored the sample size, called this normal distribution with the mean and standard deviation. Technically, that's incorrect. I do not know the actual average temperature in each month. I do not know the actual standard deviation. We don't have data. We haven't been measuring since beginning of time. We just have the last 83 data points. When you have a sample from a population, technically, that's a t-distribution. That's not a normal distribution. So what we're going to do here is analyze the data the way you should analyze it, rather than using a normal distribution, using a t-distribution. And the answer is going to be very similar, because when you have 83 data points, it's almost a normal distribution. Not quite, but almost. Let's start out with June. Is June going to break 100 degrees Fahrenheit? Well, I know the mean, I know the standard deviation, I know the sample size. To find out if it's going to break 100, I do a t-test. So again, June is a normal distribution. I've got a mean of 92. I'm looking for the number 100. What is the distance of 100 from 92 in terms of standard deviation? That's the t-score. That is, how far is 100 from 92 in terms of standard deviation, It's 1.6812 standard deviations away. Go to a t-table or a stat track and say I have sample size of 83, meaning 82 degrees of freedom. I have a t-score of 1.6812. What is the area of the tail? I use a negative number because I want the area of the tail. This actually finds the area to the left of your t-score. That tail is 4.826%. So from the data, that's the chance that it's going to break 100 this June. Now that answer is a little bit different than what we calculated before. That's because before we used a normal distribution. A t-distribution is slightly different than a normal distribution when you have 82 degrees of freedom. It's close, but it's a little bit different. What's the 90% confidence interval? Again, in StatTrack, I can say I want the tails to be 5%, 82 degrees of freedom. What's the t-score? Now, previously, the z-score was 1.644. This is the t-score. It takes sample size into account. When I have a t-distribution, the t-score goes up a little bit. So rather than being 1.644, it's now 1.663. A little different, but pretty similar. This would be the correct way to analyze it. So based upon that data, I want to go left and right of the mean by 1.66365 standard deviations, meaning that I can be 90% certain that the high in June will be somewhere between 84.5 and 99.9 degrees Fahrenheit. That's a t-test. Now suppose instead of using all the data, I just use the last 5 years of data. Again, climate's changing, temperature's changing. If I use all the data, I'm using old data. They may not be valid anymore. Let's just use the most recent 5 years. If I use the last 5 years, again, I've got the data. Over here, just take the last 5 years of data. It has a mean, standard deviation, sample size. If I want 5% tails, I'll go to StatTrack and say the tail is 5%, 4 degrees of freedom, sample size is 5. What's the t-score? Now the t-score changes. T-score changes with sample size. Instead of being 1.66, it's now 2.13. So now I want to go left and right 2.13 standard deviations from the sample mean. And that gives me, based upon the last 5 years of data, the 90% confidence intervals between 94 and 104 degrees. So there's a lot of ways to analyze the data. That's based upon the last 5 years. Another question you might ask is, okay, this is the average using all the data, confidence interval. Here's the confidence interval using the last 5 years of data. It certainly looks like we're warming up. Are the last 5 years warmer than the first 5 years in the data set? Well, that's comparing two populations. I can do that with a t-test, but that'll be the next lecture. This lecture we're just focusing on a single population. That's the temperatures. Another example. Suppose I roll 10 six-sided dice. What's the chance that the numbers will be bigger than 44? Well, one way to do that is convolution. I know what the probability is for rolling a single die. Use convolution to get 2 dice, 4 dice, 8 dice, 10 dice, then just add. What are the numbers 45 and higher? And this is offset by 1. So the first entry in MATLAB is a 0, second entry is a 1, third entry is a 2. So 46 means 45. This is adding up the numbers 45 and higher, and I get 3.9%. That's this area right here. Can I get the same answer using a t-test? Well, the first thing you need is collect data. So what I'm going to do is pick a number like 10, roll the dice 10 times. The bigger the number, the better the results. But again, if this is industry, each time you collect data that costs money, pick a reasonable number. Suppose I pick 10. So here in MATLAB, I roll the dice 10 times. I get a mean, I get a standard deviation, I get 8 degrees of freedom, sample size minus 1. So this time when I ran it, I got a mean of 33.6, standard deviation 5.18, and 9 degrees of freedom. Again, your answer is going to vary every time you run this. It's a random process. But suppose I got these numbers. What do I do with them? Well, to find the probability of rolling 44 or 45 or higher, I'll find the area of the tail. And again, I'm looking for the number 45. But this is a continuous distribution. Here's 45, here's 44. I'm going to take the midpoint, 44.5, and find the area of the tail to the right of that. So I want to find the t-score. How far is 44.5 from the sample mean in terms of sample standard deviations? And for me, I got 2.13. From StatTrack, I can then say my sample size is 10, meaning 9 degrees of freedom. My t-score is 2.1003. I want to find the area of the tail, so make that negative. Calculate, and StatTrack spits out the answer, 3.2543%. Again, almost the correct answer. The correct answer from convolution was 3.9%. Here with the sample size of 10, I'm pretty close, 3.25%. So again, what you're doing is very similar to what we did with the normal distribution. I'm using a t-score, calculated almost exactly the same as you did the z-score. But to interpret it, I need to use a t-table. The t-table takes sample size into account. So that was the probability that a given die roll will be bigger than 45. It's about 3.9%. Suppose instead I said, what is the average of 10d6? What's the probability that the average is more than 44? So this is a kind of subtle difference. The previous case, so again, this is a subtle difference. Here I'm asking about populations rather than individuals. I want to know, rolling 10 six-sided dice, it does have an average. That's just a number. Can I estimate that average from my data? When you're estimating a number, like the population's average, the more data I have, the more precise I can know that answer. So for population questions like this, I do divide the variance by the sample size, or equivalently, divide the standard deviation by the square root of sample size. So in this case, I collect the data. I've got a mean, standard deviation, but now I divide the standard deviation by the square root of n. So this has gotten smaller. I now want to know how far is 44.5 from the sample mean in terms of standard deviations. It's 6.6 standard deviations away. Converting to a t-score, or the t-score to a probability, going to StatTrack, I now have 6.64 standard deviations. Probability, area of the tail, is 0.000047. So there's a 0.000047% chance the population's average is bigger than 64. Now what's going on is for an individual, like a single die roll, I've got a spread. That doesn't change. Every time I roll the dice, I'm going to get a different answer. It's got variability. Standard deviation is like a measure of the spread. That's the variability. Here's my number 45. I want to know this area right here, 44.5. That area doesn't change. The sample size goes to infinity. In contrast, the population does have an average. I don't know what it is, but I can estimate it based upon my die rolls. As the sample size increases, the spread gets tighter and tighter. With a sample size of 10, I'm right here at the blue line. Sample size goes to infinity. It becomes a very, very narrow normal distribution. There is still a chance that I had bad data. I sampled a bunch of data. I've got 10 data points. I might have gotten data down here. Could happen. So it's possible that the population's mean is over here. Not likely, but it is possible. And I think it's right around 35-ish. Based upon my data, it's really bigger than 45. The probability of that is 0.000047, but there is a chance. Another question. What is the 90% confidence interval for rolling 10 six-sided dice? Again, when I roll 10 six-sided dice, there's a spread. I sometimes get low rolls, sometimes get high rolls. Where is 90%? How far left and right do I have to go to capture 90%? Well, to figure that out, I need to find the t-score. How far is the mean? How far is the threshold from the mean in terms of standard deviations so that each tail is 5%? That's a two-sided test. From StatTrak, with 9 degrees freedom, 5% tails, the t-score is 1.83311. So we need to go left and right of the mean by that many standard deviations. Based upon my data, 90% of the time, I'll roll numbers between 24.08 and 43.11. That's for a single roll. You're always going to have some variability when I roll the dice. A different question is, what is the average of 10 six-sided dice? That's a population question. Again, it's just a number. I don't know what it is, but as the sample size goes to infinity, I'll have a better and better idea for what that is. In this case, I take the standard deviation calculated in MATLAB, divide by the square root of the sample size, or equivalently, take the variance, divide the variance by the sample size. And what I get is this for range. Again, 10 six-sided dice, the average is actually 35. Based on my data, I don't know what it is, but I'm 90% sure it's between 30.5 and 36.6. And not surprisingly, 35 is in that range. So, looks like these dice are fair. That's with dice. Another example. In previous lectures, we looked at 5-card stud poker. For example, here's a program that we had previously. It deals out, in this case, 10,000 hands of poker and counts. How many times I got a royal flush, straight flush, four of a kind, and so on. So every time I run this, I get a different answer. Increasing that to 100,000 hands and counting. How many times I get a straight flush, four of a kind, full house, and so on. This is what we calculated using combinatorics. Well, if I do a Monte Carlo, I can count how many times I got a straight flush, four of a kind, full house, and so on. Suppose I don't know what the actual odds are. Can I calculate those odds using a t-distribution? Well, let's look at full houses. So if I want to know how many times I'll get a full house when dealing out 100,000 hands of poker, that's an individual question. What I'll do is I'll take the data that I had before. That's 124, 144, 153 hands out of 100,000 got a full house. I will then find the mean, find the standard deviation. The spread for the hands dealt, that'd be an individual question. I'm going to take the t-score for 5% tails. From StatTrak, that's 2.91999. That's for sample size of 3, 2 degrees of freedom, 5% tails. Go left and right of the mean, that many standard deviations, and what that says is somewhere between 96 and 183 hands should be a full house. And I can check that. Going back to MATLAB, so if I increase that to 100,000, this should be somewhere between 96 and 183. So let it run for a while. It takes about 10 seconds. So 96 to 183. Find the MATLAB here. That's what I got, between 96 and 153. Let's try it again. Again, I won't get it all the time, but 90% of the time, that number should be between 96 and 183. Again, 133, that's in that range. Okay, so that's an individual question. How many times do I get a full house? And that's kind of what the PDF looks like. I've got a mean, I've got a standard deviation, the normal distribution, it's actually a t-distribution, looks very much like a normal distribution. There's my left tail, 5%. Here's my right tail, also 5%. And 90% of the time, I'll have numbers in this range. Slightly different question. What is the probability of being dealt a full house? Now from enumeration, I know the actual odds are 145 in 100,000 hands. So that's the number I should get. When I deal out the hands, these are the numbers I got. To find the population's average, again, this is just a number. I don't know what it is, but I can estimate that number. As the sample size goes to infinity, I know what that number is precisely. With only a sample size of 3, I'll then take the standard deviation and divide by the square root of sample size. Again, divide the variance by the sample size, the standard deviation by the square root of sample size. T-squared stays the same. I have a sample size of 3, 2 degrees of freedom, that's 5% tails. Now this tells me that the probability of being dealt a full house, again, population question, is somewhere in this range. I don't know what it is, but I'm 90% certain it's between 115 and 165. And surprise, surprise, the actual odds lie in that range. Again, I don't know what it is based upon that data, but I can bracket it. And again, this is for the population. The population's average is just a number. I don't know what it is, but I'm 90% certain it's in this range. And you got to tell me this number. If I want to be 100% certain, I think the probability is somewhere between minus infinity and plus infinity with 100% certainty. That's the t-score. T-score goes to infinity as the area of the tail goes to 0. To get a meaningful number, I've got to say 90%, 99%, 99.9%. As the tail gets smaller, the t-score gets bigger, and I spread out the confidence interval. So if I want to be really, really certain, I've got a pretty big confidence interval. The tighter I make this, the less certain I am. So that'd be a second example using what we did before with Monte Carlo. And again with Monte Carlo, every time I run the experiment, I get a different answer. That's giving me information. The way you use that information is a t-test. So again, we kind of noticed that before. Monte Carlo kind of gives you an idea. The way to analyze it, you need to use a t-test. Okay, third example. Now, in a previous lecture on uniform distributions, we used a uniform distribution to model resistors. If I have a 1K 5% tolerance resistor, I don't really know what the resistance is. From the data sheets, it says it's somewhere between minus 5% and plus 5% of the nominal value. I don't know what it is, so one way to model it with Monte Carlo is to assume a uniform distribution. The resistor can have any value between minus 5%, plus 5%. No reason to assume one value is more likely than another. That's the uniform distribution. Well, here's a question for you. Is that assumption correct? Do resistors really have a uniform distribution? Well, to answer that question, I need data. And once I have the data, I need to look at how do I analyze that data. Well, there's a couple of ways to analyze it. If a uniform distribution is correct, then the average should be 1,000 ohms. If I collect a whole bunch of data, what's the probability that the population's average is 1,000 ohms? Again, that's a population question. If this is a uniform distribution, the variance should be 28.86 ohms. The variance is the spread divided by 12, spread squared. Is that correct? Well, given some data, I can check each of those. So the first step is to collect some data. Here I went out and took a bunch of 1,000 ohm resistors, measured the resistance. There's the data I got. Once I get that data, let's analyze it. So let's look at the mean being 1,000 ohms. Here's my data. I can find the mean, find the standard deviation. This is a population question. So I want to know, is the population's average 1,000 ohms? Since this is a population question, I divide the variance by n, or the standard deviation by square root of n. So this is my 90% confidence interval for the population's average. If it truly is the uniform distribution between minus 5% and plus 5%, it should be 1,000 ohms. What I'm getting is this. The population's average is between 994 and 992 ohms, is this blue curve. So basically I can say this 1,000 ohms is outside the 90% confidence interval. Nope. This is not a uniform distribution between minus 5% and plus 5%. So that assumption was wrong. And actually, to give you an idea of percentages, this is nominal. This is minus 1%, minus 2% is over here, plus 1%. The specs tell me somewhere between minus 5% and plus 5%. Actually, it looks like it's within 1%. So this is a difference where the word significant is different in English than statistics. In statistics, significant just means, can I tell the difference? Can I tell you that the average is different than 1,000 ohms? And yep, I sure can. So this is statistically significant. From an engineering standpoint, is it significant is a different question. Do I care that the average was 993 ohms, not 1,000 ohms? Again, this is a 5% tolerance resistor. Anything within 5% is okay by me. That's what the data sheets tell me. And I'm well within 5%. I'm within about 0.8% of the rated resistance. So this is actually better than the manufacturer's claiming. So from an engineering standpoint, no, that's not significant. From a statistics standpoint, yes, it is significant. Because statistics means, can I tell the difference? And yep, I sure can. From an engineering standpoint, do I care? That's a different question. Another way to look at it, if this is truly a uniform distribution, the variance is 1/12 of the spread squared divided by 12. Should be 28.8 ohms for the standard deviation. This is the standard deviation I actually got. Is that correct? Well, the standard deviation is actually gamma distribution. It's not a normal distribution. It can't be negative. So technically I shouldn't be using a normal distribution for this. I'm going to use it anyway. A problem though is that when I find the standard deviation, I need to have a sample size bigger than 1. Here I've got one sample, one population. I've got a single number. Is that number 28? Again, I can't do anything with a single number. I need more data. So there's a couple ways to analyze this. One way is to take the data and split it into 4 populations. I then have 4 standard deviations, one for each population. Assuming this is a normal distribution, and again it's not, it's a gamma distribution, but assuming this is a normal distribution, I've got a mean, I've got a standard deviation. It actually didn't do that correct. I want to find the mean of data and standard deviation data. It's not quite right. Correct on this slide. So there's the mean of the data. Here's your standard deviation of the data. Is the variance actually 28.86? Well, from here, I can find out what the standard deviation is. I go left and right, 2.35 standard deviations, between 1.58 and 6.2. The number that it should be, 28, is way, way, way far away. That again tells me that the variance is not 28.8. This is not a uniform distribution. Now, one problem with data is oftentimes hard to come by. Oftentimes I want more data, but the data just isn't there. If I could get more data, I could give you a better estimate of the population's mean and variance. I would get a smaller estimate for the population's mean, a smaller t-score. All that's good. But again, oftentimes data is hard to get. Again, like if you're working at a company and you're looking at products that get returned, that's the data. When stuff fails, what's the characteristic of stuff that failed or got returned by the customer? Well, ideally, nothing gets returned, so you have no data. You oftentimes will get one, maybe two products get returned. Well, that's all the data that you have. How do I get more data when the data is just not there? So for example, let's just say I want to look at the probability of getting a full house when I deal out 6 cards. Well, I can do a Monte Carlo simulation and simulate it. Each of these takes a little bit of time to run. If I ran it 20 times, here's my data. What's the 90% confidence interval for getting a full house when you're dealing 6 cards? What that means is you dealt 6 cards, take the best 5 cards. What's the chance of a full house in those 6 cards? Well, I could do a t-test. I've got the mean. I've got a standard deviation for those 20 data points, sample size. I can find the t-score. If I have sample size of 20, meaning 19 degrees of freedom, 5% tails has a t-score of 1.58. So I'm going to go left and right, 1.58 standard deviations. I'm trying to find the population's average. So there is divide by the square root of n. It says I don't know what the probability is, but it's somewhere between 792 and 820 out of 100,000 hands. That's with 20 data points. Now, I'd really like to have more data, but it takes some time to create that data. So what can I do? Well, one approach, this is done. I personally think it's fudging your data. It's not valid, but this is done, is to take your data, split it into 4 groups, then create 6 different data sets, population A and B together, A and C, A and D, B and C, B and D, C and D. It now looks like I've got 60 data points. 6 samples with 10 measurements each. With that, I can say, here's my different populations, here's the average of each group, here's the standard deviation. I can do more analysis with that. Is that valid? Well, it is done. Personally, I would call that fudging it. What you've done is you're triple counted each data point. This point right here appears 3 times in my data. Once in A, once in B, once in C. Taking the same data and copying it 3 times doesn't give you 3 times the information. It just means you got 3 copies of the same data point. So I personally think this is completely invalid. But some people do use that approach. You do find published articles where people use that approach. I personally think it's invalid, but that's my opinion. What you really need to get more data is you need more data. You need to run the experiment more. But anyway, that's a couple of examples of a t-test with a single population. A t-test is a test of a mean. With it, you can take a small sample from a population and determine the probability that a random sample will be more than a threshold, that's a single-sided test, or the range at which the next data point will lie. That's like for rolling dice. Next time I roll the dice, what's the result going to be? That's for an individual. I can also test the population's mean to find out, is the population's mean higher than a threshold, or is it within a range? That also is a single-sided test, two-sided test. If you're talking about populations, though, you divide the standard deviation by the square root of sample size. The main difference, though, between these two is for individual tests, you find the variance, as usual, that's the MATLAB function variance. For population questions, I divide the variance by the sample size, or the standard deviation by the square root of sample size. So that is lecture number 26 for ECE 341, examples of a t-test with a single population.